Hey everyone, and welcome. I am absolutely thrilled to have you here for this explainer of Almond's AI journal. If you're someone who really loves to pop the hood and see how things actually work, you're in the exact right place. Today, we're embarking on a pretty fascinating predictive journey. We're going to start with the simple elegance of straight lines and journey all the way into the dynamic world of probabilities. By the end of this, the foundational math that powers so much of machine learning is going to just click into place for you. Let's get started.
All right, so here is our roadmap for today. We're breaking this down into 5 parts. 1, basics of linear regression. 2, learning and minimizing error. 3, the multicollinearity problem. 4, the binary classification twist. And finally, 5, the power of logistic regression.
Section 1, Basics of Linear Regression. Welcome to the continuous world.
So at its absolute core, linear regression is a supervised learning technique. Now, supervised just means it learns the relationship between input variables and a labeled output variable by studying training data. Its entire job is to predict a dependent or target variable based on one or more independent variables. It's incredibly popular because it's straightforward, it's super interpretable, and honestly, it forms the bedrock for understanding vastly more complex machine learning models down the line. To ground this in reality, let's look at its 2 main flavors. First, you have simple linear regression, which involves just a single independent variable. Think about trying to predict house prices based solely on square footage. But life is really that simple, right? That's where multiple linear regression steps in. This handles 2 or more independent variables, like, say, predicting a person's weight based on both their height and their age. It's the exact same foundational math, just scaled up to handle more complex realities. But here's the catch with all of this. Reliable models require really strict rules. For linear regression to actually work properly, it relies on several core assumptions. We need independent errors, a constant variance of errors, which is a fancy term called homoscedasticity, normally distributed errors, and absolutely no hidden correlations between errors and predictors. But the biggest assumption? Linearity itself. But don't let that fool you. You can actually include nonlinear cross features or polynomial terms in your data. Why? Because the model only assumes the parameters, the actual coefficients it's learning, are linear, not necessarily the raw features themselves. Kind of a neat trick, right? Moving on to Section 2, learning and minimizing error. Time to see how this thing learns from its mistakes. Okay, so how does the model actually get better at predicting? Enter an optimization algorithm called gradient descent. The primary goal of our model is to minimize prediction error, specifically something called the mean squared error. Gradient descent tackles this in a highly efficient, iterative loop. Step 1, it calculates the gradient, or the slope, of the error function. Step 2, it updates the model's coefficients by taking a tiny step in the direction that reduces the error, and that step's size is controlled by a learning rate. Step 3, it just iterates. It loops over and over again until that mean squared error is as tiny as mathematically possible. And of course, we need to know if all that learning actually worked. Once the model is fitted, we evaluate it using a metric called R-squared. R-squared is fantastic because it tells us the exact proportion of variance in our target variable that's successfully explained by our independent variables. So if you get an R-squared of 0.8, that means our model successfully explains 80% of the variance in the data. Basically, the closer that number is to 1, the better your model has captured reality. Section 3. The multicollinearity problem. Let's look at a major data trap. All right, multicollinearity. It sounds like a mouthful, but it happens when 2 or more of your independent variables are highly correlated with each other. They're basically feeding the model the exact same information twice. And when this overlap happens, the model gets horribly confused. It suddenly struggles to isolate the individual effect of each predictor. This totally inflates your standard errors, it drastically reduces your statistical power, and it makes interpreting those coefficients practically impossible. So how do we catch it before it wrecks our model? Data scientists use a diagnostic tool called the variance inflation factor, or VIF. If you run a VIF check and you see a number over 5, or especially over 10, that is a giant red flag. A high VIF means a variable is way too correlated with other predictors, meaning your model's coefficients are currently unstable and totally unreliable. Thankfully, it's not the end of the world. We've got a practical toolkit to fix this overlap. The absolute simplest method:
Just drop one of the highly correlated variables. If you really can't do that, you can use dimensionality reduction techniques, like principal component analysis, to transform the variables into uncorrelated components. Or you could apply regularized regression, things like ridge or lasso, which mathematically penalizes the size of the coefficients to reduce their sensitivity to that multicollinearity. Section 4, the binary classification twist. Here's where the narrative completely pivots. Let's pose a totally new scenario for a second. What if we want to predict the weather in Seattle based on the temperature? Though honestly, predicting rain in Seattle feels a little bit like cheating, doesn't it? But still, in this case, we don't want a continuous number. We just want a simple binary answer. Will it be a rainy day, which we'll call 0, or a sunny day, which we'll call 1? Now, if you try to force our trusty linear regression model onto this new classification task, it breaks down entirely. The linear line will just keep going forever, outputting completely nonsensical values. It might predict a 1.5 for a sunny day, and you literally can't have a 1.5 probability. This is where logistic regression swoops in to save the day. Instead of a straight, unbounded line, logistic regression fits a beautifully bounded S-shaped curve to the data, ensuring that every single prediction stays strictly between 0 and 1. And that brings us perfectly to Section 5, the power of logistic regression. The absolute core mechanism behind logistic regression is a neat piece of math called the sigmoid function. The sigmoid function's entire job is to take the unbounded, infinite output of a linear equation and compress it. It maps it smoothly into a range strictly bounded between 0 and 1. It takes our straight line and bends it into that elegant S-shaped curve I just mentioned. Now you might be thinking, okay, so what? Well, bounding predictions between 0 and 1 is a total game changer because it gives us a natural, probabilistic interpretation. Logistic regression doesn't just spit out a raw guess. It models the log odds of an event occurring. By passing those log odds through the sigmoid function, the output becomes the literal probability of our positive class. So an output of 0.85 means there's an 85% chance it's going to be a sunny day in Seattle. But why use the sigmoid function specifically? Why not just use a simple step function that sharply jumps from 0 to 1? Well, a step function outputs discrete values, which completely breaks optimization. This sigmoid function offers a smooth transition. And more importantly, its convex nature means it has a smooth gradient. It is perfectly differentiable, which makes the gradient-based optimization we talked about earlier incredibly efficient for training the model. It just makes the math run like butter. So the crucial point is how this new logistic model evaluates its own mistakes. Since we're dealing with probabilities now, we can't use mean squared error anymore. Instead, logistic regression minimizes a loss function called log loss, usually through a method called maximum likelihood estimation. Log loss is fascinating because it heavily penalizes large deviations. It specifically and harshly punishes the model when it is highly confident about a prediction but turns out to be completely wrong. Minimizing this log loss guarantees highly accurate, reliable probabilities.
Wow, okay, so we have journeyed all the way from the strict assumptions of straight linear lines, mitigated some tricky data traps, and bent those lines into smooth, probabilistic curves. But before we wrap up, I want to leave you with a really provocative thought to chew on. If a single logistic regression model simply takes an input, applies a weight, and uses a sigmoid function to output a probability, how might combining hundreds or even thousands of these foundational models, layering them piece by piece, create the complex, deep neural networks driving modern AI today? I'll let you ponder that one. Thank you so much for joining me for this explainer, and keep exploring.